Hello everyone, I'm Haotian Wang from Stony Brook University. Today I will introduce my work Distributed Human Trajectory Sensing and the Partial Similarity Query. The ubiquitous availability of mobile device and wireless coverage has allowed for the collection of a huge volume of human motion trajectory. Such big human mobility data has motivated human trajectory analysis and data mining with many applications. There are two main properties of natural human trajectory: individuality and commonality. The human mobility trajectory in the spacetime domain is very sparse. It's unlikely that two different users at the same location in the same time step. Thus, the individuality of human trajectory suggests an important security-related application. On the other hand, data mining applications try to identify commonality among the trajectory. This common pattern and feature of the trajectories could be useful for city planning. Our work is based on individual electrical bike trajectory. The narrowband IoT module is deployed on the license plate of the bike. When we start the engine, it begins to report records every 10 seconds. The record contains the timestamp and the location. This location has two classifications. The first one is GPS location of this electrical bike, and another one is the appearance location, which is the location of this base station or checkpoint who cover this electrical bike. So we have two city scale dataset lasting about 1 month. One is the GPS location in Zhengzhou, China, and another one is appearance-based location in Wenzhou, China. We can see the number of record every day is very huge. So our goal is to find the similar trajectory or measure the similarity between the two trajectories. The traditional similarity measurements are Hausdorff distance and Fauché distance. Hausdorff distance is the maximum of distance from any vertices on one trajectory to the other trajectory. Fauché distance is the minimum of maximum distance for a traversal along two trajectories without backtracking. We test on our these two measurements on our data set using two agents in the same day and one agent in two consecutive days. We can find that both of them are sensitive to outlier. For two agents in the same day, we can find half of their distance are about the radius of the city. In addition, due to huge data, the computational cost is very high. So in our work, our contribution mainly focus on three aspects. First, we develop new concept of partial trajectory similarity measurement. It is robust to outlier. Second, we propose the random sampling to create a sketch. It can reduce the computational cost and the storage capacity. Third, we introduce how we use this framework and provide some advice for the practitioner. First, we look at our first contribution. Here is our model. So given the trajectory set, each trajectory is a sequence of pair of time step and location. The problem is given a query trajectory, we want to find all the trajectories that are similar with the query one. Now we define the new similarity measurements. The first one is time-sensitive similarity. It measures the degree of two agents appearing in the same checkpoint at the same time slot. So the formula is like this. We use the number of same tuple in two trajectories divided by the minimum length of two trajectories. If this ratio is larger than alpha, we say that the trajectory Ti is alpha time sensitive similar with the query trajectory Tq. The second one is called order sensitive similarity. It ignores the time but cares about the order of visited location. It captures the shared sequential pattern into trajectories. Thus, we use the longest common subsequence in two trajectories divided by the minimum length as their order sensitive similarity. The last one is order insensitive similarity. It considers the number of common checkpoints visited by two agents, regardless time and order. So we only focus on number of common checkpoints in two trajectories like this. So if this ratio is larger than alpha, we say the Ti trajectory Ti is alpha order insensitive similar with TQ. So we can see these three similarity measurements are robust to outlier because it ignores part of the trajectories. Next, let's look at our sketch to reduce the computational cost and the storage. So it's a huge storage if we collect all the records. Thus, we can set a sample probability p. It means that in each time slot, each checkpoint can be activated to collect the record with a probability p. For storage, we use different data structure to store these records. So here is an example. There are 5 points in these two trajectories, and we can see 2 points are different. So when we use the random collection, the red node represents the activated checkpoint. So there are 3 checkpoints. 3 points are stored or maintained in both trajectories. Thus, the sampled trajectory are stored in this format showing below the representation, and we can see it reduce a lot of storage capacity. In addition, if we use the sampled trajectory to calculate their similarity, we can find this similarity is not influenced a lot. So in the following, we will prove their performance. Finally, we implement this framework and achieve a good performance, and we will introduce how we use it. So here are 4 steps for practitioner. First, you need to choose the similarity measurements according to your demand. And the second step, we need to set up the similarity parameter alpha. We test on our dataset. For any pair of trajectory, there are very few pairs whose similarity are higher than 60%. Thus, if we want to find the similar trajectory with a query, we can set alpha higher than 60%. It's a good threshold. So then we have to determine the sample probability. We analyze the sampling performance using the Chernoff inequality. This analysis shows that if the similarity between the original trajectory are higher than alpha, according to the variance bound and the probability bound, we can know how many points we need to maintain. In this way, we can determine the sample probability. So we can see these results. When the sample probability p goes up, the recall is increased, but the precision may go up or go down. It depends on the other parameter. So in the last step, we hope to increase the precision. We can adjust the threshold coefficient k, which is related with the variance bound. When k goes up, variance bound becomes smaller, recall is decreased, and the precision is increased. And we can see their intersection point is higher than 90%. In this way, we can find a similar trajectory with a high recall and a high precision. Last, we look at the computation cost. When we set the sample probability p less than 10%, the running time is reduced more than 70% approximately. Okay, so last here is our contribution of our work. The first we design the new concept of partial similarity and develop a random collection and to tell the practitioner how to use our framework. Thank you.